Thank you so much, Shahid, and thank you for having me back on this great CLM stage a second time today. So today I will talk about systems engineering. And systems engineering is a well-established approach to designing complex products, taking customer requirements and bringing them into a product that will satisfy those requirements. Now, I will try to explain how systems engineering and CLM fit together. Another way of saying that is I would like to explain how organizations can move from an engineer-to-order approach towards a configure-to-order approach. So the products that we are dealing with are complex products. So I have included here a couple of examples from our customers of what this means. This could be an MR scanner from Philips. It could mean a complex printing machine from Heidelberg Druckmaschinen, or it could be a complex set of components that makes up an electrical switchgear from ABB. So this is the type of systems that we will need to design and engineer. And what we see, of course, is that there are a lot of variability in these products. So the question is, how do you manage that variability when you have a systems engineering approach? Yesterday, Johan presented a quote from Gartner, and it stated that within a few years, quite a lot of manufacturing companies, according to Gartner, will have to look at CLM. They will have to look into how they can change their engineer-to-order products to be more efficient by using the CLM approach. So I'm going to use a silly example, and I know everybody is saying, well, t-shirts are not what we do. We do helicopters or wind turbines. But in order to explain the concepts, I need something that everybody understands and that is sufficiently simple that I can sort of use it as an example. So also what Anders mentioned, the base product of a product, in this case the t-shirt, could be a t-shirt that's white. What is a variant then? Well, a variant is that you can get this t-shirt in different sizes and in different colors. Let's say that. Very simple, right? So those are the base concepts. Now, in the traditional systems engineering, where you use the V model to design products, you could say, how do you handle variability in this model? Well, you can imagine that you have a base product, in this case our white t-shirt, and in that base product you will then adapt it to the specific needs of the customer. So imagine you have a customer, he says, I don't want a white t-shirt, I would really like to have a green t-shirt, a specific color, and I need it in a size which is large. In an engineer-to-order process, you would go through the V of the V model, you would go through the different phases of refining that requirement into the constituent elements, and then on the other side of the V, you would validate that you have done every step correctly. And out at the end, you will get a green t-shirt. You will maybe give it a part number or some unique identifier that means that now you have this particular variant available. Now, how would you do this then? How would you build a new variant? So imagine that you had the 4 existing t-shirts. 2 of them are yellow, 2 of them are gray. And now what do you do? Well, the traditional approach is that you try to find the variant among these different ones you already built. You find the one that's closest, resembles the one that's being required, and then you copy that. You copy the bill of material, you copy the CAD files, you copy whatever artifacts that are needed to build that product, and then you adapt that. You change it and modify it, and at the end you have a new copy with all the artifacts needed to produce green t-shirts. That's the engineer-to-order approach. And if you look at the benefits, or not the benefits, the problems with that, one problem is that it's quite costly to offer many different variants. Another problem is that it can take a long time from a customer comes with his requirements, with his request, until you can return a quote and a price and whether it's even possible. And finally, you will also see that if there are changes in the process, maybe there's an initial set of requirements, but then later the customer comes with some changes to those requirements, a lot of work has to be redone, and that is, of course, inefficient. The configure to order is a different way to deliver products that have a high degree of variability. The basic idea is that you decompose, modularize the product, and you build up the solution that matches the requirements by selecting those different components in a certain configuration, and then you can deliver that efficiently. So in a way, you have predefined the set of components and the ways that they can be combined that will make up the product offering that you have. I want to point out that it's not black and white. If you go back and watch the presentation from yesterday from Man, there was a very nice overview of the different ways or the different shades between pure ETO and pure CTO. There are some other variants in between there where you do more or less of CTO. But the benefits and the reasons why people are interested in going down in the CTO path is that it will improve profitability. Basically, there's lower overhead in the producing individual variants. You will find that the time to do a quote is much faster. You can tell readily what's available and what's not. And finally, you will basically get a better customer experience. You can immediately reply, you can immediately feedback what's possible and what's not possible. So how do we move from our ETO processes going through the V for every single variant, every single customer request? How do we move towards the CTO? And that's basically what I'll try to explain to you for the remaining of this presentation. The very first step is to introduce a notion of features. So a feature is a characteristic of the product. It's a way to classify the product in parameters that are understandable from the customer's perspective. So in our T-shirt model, it could be the color and the size. In the wind turbine example that we just heard, Anders mentioned the height of the tower, the amount of power it produces, and things like that. Those are characteristics of the product, and you have to start codifying those in terms of using features. Once you have established those feature codes, you have to make sure that they are established across the entire organization. It's not just an engineering discipline. These are the things that eventually will be priced. They will be the ones that the customer orders. It will be the ones that you send down to your manufacturing. They will basically be the language of communication for collaborating across the different functional areas within an organization. And that's exactly the CLM promise. If you introduce features, you introduce a model. Anders also talked about, and Florian talked about bringing the commercial and engineering rules within a consolidated model. We have our VT technology. We can compile the result of all those rules into a efficient representation of the single source of truth. And then you can use that information to optimize and validate your products. So that's the CLM. But okay, so how do you get there? Before I dive more into that, I think there's an important terminology aspect that I need to clarify. When you are in the systems engineering space, when you are in the PLM space, you will often hear about configuration management. How do we do configuration management? I'm talking about configuration lifecycle management. You'll notice that they're quite resemble each other. I want to point out that there's quite a large difference between them. And the difference is back to the word configuration. When you talk about configuration management, and I put the definition here, I'm not going to read it up, you can look it up on Wikipedia, but basically, when you talk about a configuration in the context of configuration management, think of that as a version of the artifacts. It is that you have taken a snapshot of all the documents and the BOM and what else you have, given it a number or an identifier, and that is sort of a configuration. This is a contrast to the CLM definition of a configuration. In there, it's basically a selection of values for the features. So a way to illustrate this with our t-shirt example, and again, I know this is overly simplifying, but if you imagine that you have a t-shirt, here's a medium one in yellow, and you do a configuration change in the context of configuration management, you could imagine that you got a new sub-supplier and the shade of this yellow color has changed ever so slightly. That is a configuration change from the configuration management perspective. From a customer perspective, this is still a yellow medium t-shirt. And this is unlike if you did a configuration change in the CLM context. Here we would imagine that you change from a yellow to a green and maybe the size from a medium to a large. This was just to make sure that we are all on the same page, because I know when talking to engineering, then this is a common area of misunderstanding. So back to our t-shirts, how do we get from managing variants in a systems engineering perspective? So we have now introduced the notion of having features. For our t-shirt, we can imagine we have a size and we have a color. And those, of course, have the values small and medium and yellow and gray. We will also, and then the configuration will then be, as shown there at the bottom, yellow small, yellow medium, gray small, gray medium. And another concept that we need to introduce is that we need to introduce the concept of a configurable BOM. Sometimes this is called a 150% BOM, sometimes it's called a generic BOM. The configurable BOM is a bill of material structure where there are logical statements that specify when to include or not include parts and assemblies in that structure. Now, again, this example is overly simplified, but basically what we have here is that we have 4 different t-shirts, and they have a condition that specifies for when you select one of those 4 based on the features that the customer has selected, color and size. Now, here's the order flow in a configure-to-order process. You have a model of your product offering called a product model, features and some rules. I will not talk very much about the rules today. Once you have that, you build a configurator. That configurator exposes those choices to a customer or a reseller or whoever is going to configure a product. Here we have our color and size. Once you have selected values for those features, maybe I want a yellow and a medium-sized t-shirt, then I can apply that selection to my configurable BOM, and the system will automatically spit out that then this is the assemblies or the 100% BOM, the order-specific BOM that I need to be able to deliver that particular configuration. So how do we move from the engineer to order to the configure order? We have our features in place, and the first step could be just to start using those features as part of the V model. So the requirements as they come in from customers can often be translated to feature statements. I want my t-shirt to be this and this. That's basically is color is equal to that, size is equal to that. And then you can imagine going through that V model with that feature content. Now, that doesn't do very much in order to optimize the process, except it now starts to allow you to filter and search and find other variants more quickly, because you can search and filter based on the feature content. The next step could be to say, okay, we will build up a logical model, and we will use that model to guide the user, but we will allow the user to select special values. So I know I have yellow and gray t-shirts, but I will open up and allow the customer to select this value in the dropdown called special color. And when that is selected, the configurator will basically say, fine, what color do you want? And the customer will just type in what his requirement is. This is a very sort of simple approach to ETO, but it's something we've seen quite a few of our customers embrace and use. When this happens, there is a special process triggered when this order is being placed. It doesn't go through the automated path that as I showed before, but instead it will trigger a process where an engineer has to look at this. And then he has to decide, is this something I actually want to do or not? And if it is, he needs to do the engineering to update the bill of material so that we can deliver that particular variant to the customer. Now, here's the trick to get towards more configure to order. What he can also choose to do is to extend, enhance, expand this logical model that drives the configuration process. He can then introduce a new color in our feature for colors. He can introduce the large because we didn't have that before. And maybe he adds some rules to dictate what is the conditions under which we can get this green t-shirt. And once he has done that, then the screenshot there on the right should be updated, and the next time around a customer comes along, he can then choose a green color among the choices in the dropdown. And then you have turned this ETO, slow-moving process you did when you introduced the green t-shirt, you have basically turned that into the fast-moving, efficient process of ordering the green t-shirt. So you could say if that's all he does when he introduced the green t-shirt is to introduce one specific variant, then this will be a very slowly evolving growth of the variants. You could probably imagine that when he introduced the green color, he should at the same time consider whether that applies to all the sizes or only to the large one that was required by the customer. So what often happens and typically happens is that you do an analysis and you say, hey, okay, we can do green t-shirts, but we can do it in all sizes. So we are not just introducing one variant, but potentially hundreds or thousands of variants by just extending that color by that one value. So this opens up another question. How do we validate when we are no longer talking about a single variant? We suddenly are looking at thousands and billions of combinations that we need to validate, need to make sure are correct, every single one of them. This is, of course, a big challenge compared to the validation going on in the V model of a single instance. If we look at typical products that we deal with, and some of the ones I showed before, you'll find that they exist in enormously big numbers of combinations. Here's a Range Rover Sport, and that you can get in 10 to the 21 valid configurations. There's 10 to the 21 different ways you can select the values for the features that will produce a correct and working car in the end. How do you validate that? And the approach that you take to that validation is that you now have to validate that this logical model with the features and rules and this configurable BOM, that they together fit together, so that whenever I have a valid configuration according to my product model, and I apply that to my configurable BOM, what comes out will be a valid bill of material that will be working and will be legal and will be as it should be. The way we do this is a process where we use our VT technology. We build solution spaces for the product model and for the bill of material, and we compare them. So the approach is that you take the logical model, you build a solution space by compiling it with our VT technology, and what that gives you is a set of valid configurations among all the possible configurations. So I try to illustrate that here on the right with this green circle indicating that some configurations are not valid combinations according to the rules in my product model. And we can do the same thing with our bill of material. We can take those statements that was on the configurable BOM, we can compile that, and that will give us, I should say, you need a bit more information about what makes up a valid bill of material. Things like, I have to have 4 wheels and I have to have 1 engine. But once you have that, you can build a solution space that represents all the valid bill of materials. That solution space will typically be different from the solution space that came out of the product model. In this case, you can see that they sort of overlap. And if you look at this, you'll find that those configurations that sits there in the blue circle but are not in the green circle, they are valid bill of materials, but they cannot be sold. There's no configuration out of the product model according to that, which leads to that particular bill of material. So in a sense, that's over-engineering. It could also be a mistake, and maybe we had to change the product model so that it allows this, but this could also be that you have engineered stuff in the bill of material that is not needed. There has been a marketing rule that says we're not going to offer heated seats in Australia. And suddenly that was not available for engineering, and they built that option in, but it's never going to be sold. So that's a problem. The other challenge, of course, is if you have this situation where there are valid configurations that leads to invalid bill of materials. So that's an even more serious problem, because this means you take orders, you allow customers to select combinations, take the orders, send them down, and then when it hits some late stage, maybe even in manufacturing, you realize that you're missing parts or you have too many parts. But the big problem, of course, is if the bill of material is missing parts. You have a car with no wheels. So this is certainly something you want to catch. So the solution spaces are super powerful to do this type of analysis, because they can do it over these very large numbers of combinations, 10 to the 21 possible combinations. That's what the VT technology can handle. So that's how you do validation. You can do more with the VT technology. One of the things that we have also looked at is how you can use the solution spaces to optimize the bill of material. So here's an example from a company we worked with at some point. They looked at the component that sits right behind the steering wheel of a car, and they looked at the variability of that component. And the variability of that component depends on various selections that you choose in the configuration, with or without lane assist, with or without adaptive cruise control. There was something about heated steering wheel. There are a number of parameters that all affect this component. And what was found was that there are 96, there were at that time 96 different variants of this particular component. So that seems like a high number. And if you then start looking at the statistics and what is actually being selected and is being put on the cars out there, you will find that only 7 of those variants make up for 80% of all the sold configurations. So this type of analysis of looking at the solution spaces, in this case focusing on the part of the bill of material that had to do with this component behind the steering wheel, that allows you to do optimizations. Now, how can you then simplify this? How can you reduce the 96 down to a smaller number? Well, one simple way is to start writing rules that will link some of these together. You can make them less independent. So you can make it so that whenever you choose the lane assist, you always get the assisted cruise control. They always go hand in hand. So either you have both or you have none. And therefore, instead of 4 combinations, you're down to 2, and that will reduce the number of components. So that was what I wanted to talk about. I hope I've given some insights into how systems engineering with the traditional V model can be extended to handle configurable products, where you use a configuration model to define the possible choices that can be made, and how you then validate that against the configurable BOM, and thereby efficiently are able to deliver many different variants. And I think an important point here is that you can do this change from ETO to CTO. You can do it in a slowly evolving manner. It doesn't have to be sort of like a big bang disruptive project. You can start introducing features in your organization. You should probably also start looking at decomposing the product into modules and describing those modules using features and product models, because then you can create the overall product model by combining smaller components into a solution, not very differently from what Anders just talked about, building up a system with wind turbines, but this will certainly apply to also simpler products than that. So a key point is that our VT technology, we believe, is a key enabler for this, because that is how you can optimize and validate that you do this correctly. So that was what I had on my mind today, and with that, Shahid, over to you.